Hello everyone, my name is Jinyi Shangguan. I'm from MP Infrared Group. Today I will talk about to spatially resolve the borderline region of AGNs with near-infrared interferometer, and therefore to measure the mass of the supermassive black hole. Yes, the supermassive black holes are found prevalent in the center of the galaxies, and to measure the mass of the black hole is one of the most important jobs. And this has been done for the galaxies in the nearby universe, including our own Milky Way, by measuring the dynamics of the star or the gas. But if we go to the cosmological distance, it's actually very difficult to resolve the so-called sphere of influence of the massive black hole. And therefore, studies mainly focus on the so-called active galactic nuclei, or AGNs, the accreting black holes. And they are characterized by the broad recombination line with line width 1,000 to 10,000 kilometers per second, implicating that these ionized gas are very close to the supermassive black hole. In fact, these borderline regions are also very small on the sky, cannot be really resolved by ALMA or even ELT. But astronomers realize that the light curve of the emission line lag behind the light curve of the continuum, which comes from the accretion disk. Therefore, by measuring the time lag between the two, we can estimate the size of the borderline region. And after more than 2 decades of study, we now have a lot of understanding on the borderline region. But there are still a lot of questions unclear. For example, the real geometry of the BLR and the dynamics, the inflow and outflow, which has fundamental implication on the accretion and feedback of the black hole, and of course also to measure the mass of the supermassive black hole. Therefore, to spatially resolve the BLR is very important. And this job has recently been successfully achieved by the near-infrared interferometric beam combiner called gravity. This is mounted on here on the VLTI on ESOPER now. And our first target is the famous 3C273. It's a broad partial alpha line redshifting to K-band, and we use the continuum of the AGN itself as a phase reference. Therefore, we measure the differential phase of the emission line. We find this S-shaped characteristic signal, implicating that the blue and red part of the BLR offset differently from the center of the continuum. And therefore, we find the borderline region is rotating perpendicular to the jet, which is quite consistent with our physical expectation. And after the success of 3C273, we start a large program to observe several nearby bright AGNs. IRAS 0949 is the second source will accumulate enough exposure to extract the differential phase signal. And you can see clear the velocity gradient of the photocenter. And very interesting that the entire BAR seems offset from the center of the continuum. Although there could be different interpretations, we believe the simplest explanation is that we find the continuum emission is quite asymmetric. Therefore, the photocenter of the continuum is offset from the BLR. However, the mass distribution of the dust intercept medium could be well symmetric around the black hole. And up to now, we already have 3 objects resolved with BLR. And for the details of NGC 3783, please watch Taro's talk. And by model the gravity data, we can infer the details of the BLR properties using a dynamical model. And we can measure the black hole mass and compare this with the geometry of the BLR with the reverberation mapping data. For example, we can put the 3 targets on the famous Radius-Luminosity relation, and seems that they are pretty consistent with the reverberation mapping results. And we also find that the light-weighted BLR tend to be slightly different from the lag-weighted BLR radius, which is understandable depending on the geometry of the BLR structure. And this is my summary. You are very welcome to read our papers. Thanks.